All right, today we are going to be taking a look at section 5.1, which is over trigonometric identities. Now, these are the identities that we're going to be using today, and you should have these on a trig identity sheet that you're going to be given or that you already have. Now, if you don't have that, it will be this sheet right here, and this will also be on Canvas if you need to print it out. The only ones of these identities that we're going to be using today are right here. All the others we'll get to on a later day, but for now, just those. So let's go ahead and take a look back at our notes. So our trig identities that we're going to be using today are the reciprocal identities, the quotient identities, which on your trig identity sheet are called ratio identities, and then also our Pythagorean identities. So let's start with our reciprocal identities because these should look familiar. We've talked about reciprocal functions before. We know that sine and cosecant are reciprocals. We know that cosine and secant are reciprocals, and we know that tangent and cotangent are reciprocals. So these are our identities. So sine theta equals the same thing as 1 over cosecant theta. Therefore, cosecant theta equals 1 over sine theta. And then we have the same thing for the other pairs of reciprocal functions. Now, one other thing to note about these is that our reciprocal identities can be used as singles or squared. And what that means is that these identities right now are given to us as singles. So it's a single sine theta, a single cosecant theta. However, you can use this identity as squared as well, meaning you could have sine squared theta would equal the same thing as 1 over cosecant squared theta. So those can be used as squareds just as well as singles. Now notice that the square goes between the sine and the theta. It does not go all the way at the end. So those can be single or squared, and so can our quotient identities. Now, like I said, on your identity sheet that you have, those are called the ratio identities. And it's the same thing. Quotient is the answer to a fraction problem, and ratio means fraction. So same thing. They're both referring to fractions. Now, we know that tangent, what we did before, tangent was always, when we did our unit circle, y over x. So that's tangent. However, we also learned that that sine was the same thing as y, and cosine was the same thing as x. All of this is on our unit circle. Well, if y is sine, then that could be put here, and if cosine is x, that could be put here, and what do you know? That gives us this identity right here. Tangent theta is the same thing as sine theta over cosine theta. Now you always want to make sure that you include the theta because we're talking about tangent, sine, cosine, whatever, of a specific angle. That angle is not stated, but it's represented by that theta. So don't simplify and just use tangent, sine, cosine. Always write it as tangent theta, sine theta, cosine theta, or whatever. All right, then we also have cotangent. Well, if tangent is sine over cosine, and cotangent is the reciprocal of tangent, then that means cotangent theta could be whatever tangent theta was flipped over, which cosine theta over sine theta. So that gives us our second reciprocal, or quotient or ratio identity. Those can also be single or squared. So that means that not only can we use it like this, but we can also say that tangent squared theta is the same thing as sine squared theta over cosine squared theta. And the same thing with the other one. So those can be single or squared as well. So the next we're going to get to is our Pythagorean identities. Now, Pythagorean identities is not really the Pythagorean theorem. It's related, it's similar, but it is not the same thing. So our most used Pythagorean identity is going to be this first one. And on your identity sheet, you are given these first three right here. So those are the only ones that are listed on your sheet. However, these other ones that I have in the notes are simply variations of each one of those. So if we take this first one, so this is probably our most used Pythagorean identity. if we take that and we try to modify it a little bit, so if I take that identity and I subtract cosine squared theta from both sides, then we end up with this right here. So it's just a variation of that original one. Then if we look at the third one in that row, that's that original Pythagorean identity, but this time I have subtracted sine squared theta. And so I subtract it over here as well. And so that gives me cosine squared theta equals 1 minus sine squared theta. That gives me that right there. So those other two are just variations of the one in the first column. The same thing for the other rows. So if I take this next one right here, tangent squared theta plus 1 equals secant squared theta, and I manipulate that a little bit, I can turn it into either one of these. So those are both variations of the original. And then the same thing with the third row. If I take this and I manipulate it, if I subtract 1 from both sides, I'll get this. Or if I take that original and I subtract cotangent squared from both sides, I end up with this. So again, variations, which is why on your formula sheet, you're only given the originals because they can always be manipulated to get the other ones. So these are really the only ones that we want to focus on because we can create any of the other ones from those original three. Now, before we even get into using our Pythagorean identities, we're going to go through a few problems that are very similar to what we did back in chapter 4. So this really isn't going to be anything that new. So we are given that cosecant theta equals 7 over 4. And if you remember back from chapter 4, that means that this is really giving us two sides of a triangle. If I have two sides of the triangle, I can find a third side, and then from that, I will be able to find cosine theta for that triangle. Now, for this problem though, they only give me the value of one trig function, so I don't have anything else to try to narrow down, is it in the first quadrant, second quadrant, third quadrant, or fourth quadrant. Therefore, if I'm only given one value, I'm not told that sine is greater than 0 or less than 0 or anything like that. I'm just given one thing and told to find cosine. Then I'm not able to narrow down a quadrant. So all I'm going to do is just create a random triangle, and then I'm going to find that third side. So I'm going to go ahead and draw my triangle. Now remember, back in chapter 4, we were always dealing with right triangles. So, and if I'm going to find that third side, then we're talking about opposite, adjacent, and hypotenuse again. So then we're going to create our theta somewhere. Doesn't really matter where. So if I do my theta, actually, I'm going to redo this triangle to match the one I have in the notes that are on Canvas. So in Canvas, I have a triangle that is facing this direction. So here's my right angle, and then I'm going to make my theta here. Now we know that cosecant is the reciprocal of sine. So then if sine is y over, actually, we're not going to do that because we're not doing the unit circle. So sine is opposite over hypotenuse. Then that means cosecant is hypotenuse over opposite. So we have the hypotenuse of this triangle is 7, and opposite theta is 4. So then we just need to find this other side. Well, remember, your hypotenuse is always going to be C, and so that means 4 is either A or B, and the other side is the other one. So let's go ahead and make the one that we're looking for A, and the 4 will be B. So we have my A, B, and C. So that means I can do Pythagorean theorem to find the third side of this triangle. So if I have A squared plus B squared equals C squared, then that's A squared plus 16 equals 49. Then I subtract 16, and I get 33. Then to get a, I have to take the square root. So a is going to be the square root of 33, and the square root of 33 cannot be broken down. Remember, you always have to simplify your radicals if you can, but in this case you can't. 33 can only be 1 times 3. There's no pairs, therefore it's stuck the way it is. So our a then is going to be, instead of question mark, our a, is going to be the square root of 33. Now that I have the full triangle, I am able to find cosine. So remember that cosine is going to be adjacent over hypotenuse. And according to that triangle, our adjacent side is the square root of 33, and our hypotenuse is 7. And then since the radical is on the top, not the bottom, it does not need to be rationalized, and that would be our answer. So that was the same thing that we did back in chapter 4. Let's take a look at number 2, and this is actually going to be the same thing we did in chapter 4 as well. However, this time we are told that tangent theta is going to be -8 and that sine theta has to be greater than 0. So because I have those two pieces of information, I'm actually able to narrow down what quadrant it's in, which means that I'm going to have to be very careful with my positive and negative signs. So let's think about our 4 quadrants. And then remember, in the first quadrant, all 3, sine, cosine, and tangent, are going to be positive. In the second quadrant, only sine is positive. In the third quadrant, only tangent is positive. And in the fourth quadrant, only cosine is positive. So then, if tangent theta is going to be -8, well, everything is positive in the first quadrant, so it cannot be there. Tangent can't be negative there, it would be positive. Tangent would also be positive in the third quadrant, so it can't be there because our tangent is negative. So right away, just from that information, we know that we're either dealing with the second quadrant or the fourth quadrant. Then, using our second piece of information, sine theta has to be greater than 0. That means positive. So which quadrant of the 2 that's left is sine positive in? Well, sine is positive here, and cosine is positive here. So that means it cannot be in this quadrant either. It must be in the second quadrant. So we're going to go ahead and we're going to draw a second quadrant. We're going to draw it a little bit bigger though, so we have room to draw our reference triangle and fill in all the numbers that we need. So then we're going to have our reference triangle in the second quadrant, and because it's in the second quadrant, we know that the x has to be negative and the y has to be positive. So I'm going to go ahead and fill that negative in now before I forget. Now, we were told that tangent theta equals -8. But remember, tangent is y over x. So if y over x is -8, well, I can put that over 1, which means my y has to be 8 and my x has to be 1. Now, be careful though, because we said that the x has to be the negative. So wouldn't this be the same thing as 8 over -1? Why, yes it would. So then, our y is going to be +8 and our x is going to be -1. Now all we have to do is find the hypotenuse. Now, this is obviously not a unit circle, because if it was a unit circle, I could never have a side that is as large as 8. Therefore, I have to actually find the hypotenuse using the Pythagorean theorem. So I know that this has to be my C, which means this is my A and my B. And the A and the B can be switched, but the C has to be the hypotenuse. So then we'll go ahead and find our third side. So we have a squared plus b squared equals c squared. So 8 squared, 8 squared is 64 plus -1 squared is 1, and that equals c squared. So then that gives us 65 is c squared, and so the square root of 65 is C. And then again, you have to check and make sure, can that be simplified or not? And 65 cannot be broken down into anything that will simplify. So our hypotenuse is going to remain the square root of 65. Now that we have that triangle completed, we're going to go back up and see what is it that they wanted us to find. Well, they wanted us to find sine theta and cosine theta. So remember, your theta is always here at the center of your coordinates. So this is our origin, so theta will always be there. So then, if that's the case, remember, we're going to do sine theta is going to be y over r, because it's not a unit circle, so we can't just say r is 1. So then that is going to be, y was positive 8, r is the square root of 65. However, we can't leave a radical in the denominator. So if we rationalize that, it will become 8 square root of 65 over regular 65. And so that would be sine. Now we also want to find cosine theta. And if we remember back from chapter 4, cosine theta is x over r. And we have to do it over r because, again, it's not a unit circle, so r is not 1. So x, according to our triangle, is -1. And then that goes over the hypotenuse, which is the square root of 65. And that one also has to be rationalized because we can't leave the radical in the denominator. So then that would be negative, and I don't really need the 1, so negative square root of 65 over regular 65. And so that would be our sine and our cosine. So both of those problems, 1 and 2, are really kind of a review of what we did back in chapter 4. So now let's take these trig identities and really figure out what we're going to have to do with these. Now, when you start dealing with these trig identities, it's really kind of like a puzzle that you have to figure out. So we want to first come up with our strategies for how are we going to try to solve this puzzle. So you have a few things that you're going to try. So the first thing that you're always going to try is see if there's anything that you have in common. So do we have two things that are being added together, and do they have anything in common that we can factor out? So that's always what you're going to look for first. Can you factor it? Whether it's taking out a GCF or what, is there any way that you can factor it? Then, if you can't do that, then you're going to move on to the second option, which is look and see, do you have any Pythagorean identities or a version of the Pythagorean identities? Because remember, those Pythagorean identities can be manipulated into different things. So remember, we said that this one could be manipulated to give me either this or this. So we're not just necessarily looking for this main identity. We're also looking for versions of that identity. So we look for those Pythagorean identities. If I don't have a Pythagorean identity or a version of the Pythagorean identity, then we're going to move on to the third option, which is to write everything as either a sine or a cosine, because we know that cosecant can be written as 1 over sine, secant can be written as 1 over cosine, tangent can be written as sine over cosine, and cotangent can be written as cosine over sine. So everything can be changed into some version of sine or cosine. So that's always kind of our last option because it can kind of start making it look really messy at first until you start simplifying things. So that's kind of our last resort, but it usually works. Now, you can also sometimes, if those are not quite popping out, then we can kind of start thinking about it in terms of algebra. Can I use some basic algebra? Which basically a lot of times is going to be manipulating things like those Pythagorean identities. So let's take a look at number 3. Now, I'm going to go ahead and tell you now, when you first start working with these trig identities, it may possibly blow your mind. Some of us are going to latch onto this and think, this is great, I get it, this is so logical, I love it. And some of us are going to hate it. But regardless of whether you love it or hate it, you must practice these trig identities. Otherwise, it's not going to sink in. The more you do them, the more they will make sense. But if you don't practice, you are going to have a really hard time. So, even for those of you that are not very good about doing your homework, you have to do your homework for these sections. Otherwise, it's not going to sink in. Okay, so let's take number 3 and let's go through these steps. So if we want to try to factor, we are looking at these two terms because we have two terms here. This is one term, and then this is another term. Remember, terms are always separated by pluses and minuses. So we have two terms. We're looking to see if those terms have anything in common. And I'm not talking about the theta. Everything has theta because we're always referring to an angle. We're looking at, do they have any trig functions in common? So the first term has cosecant and secant. And then the second term just has cotangent. Well, none of those are the same, so you can't factor one out. Now, what we're talking about when I say factor something out is, let's say that this one had instead been cotangent. Well, then both terms have cotangent, so you could factor out cotangent theta. And so if I factor it out of the first term, that would be gone, and you would be left with secant theta. If you factor it out of this one, then you would just have -1 left over. So that's what we're talking about by factoring. Now, obviously, we can't do that to this problem because it's not cotangent, it's cosecant. So the factoring is out. Then we think, okay, do I have a Pythagorean identity? Well, no, I can't even think about a Pythagorean identity because none of these are squared. And the Pythagorean identities are always squared. So since none of those are squared, I can't even consider a Pythagorean identity. So then I'm going to go to write everything as either sine or cosine. So I'm going to convert these to sine and cosine. Well, I know cosecant is 1 over sine. So cosecant theta is the same thing as 1 over sine theta. Then that is multiplied by secant theta. And I know secant theta is the same thing as 1 over cosine theta. So this is where I'm talking about don't take a shortcut and leave out your theta. Keep those in there. Then you're subtracting cotangent theta. And we know that cotangent is the same thing as cosine over sine according to our trig identity sheet. So cotangent theta can be written as cosine theta over sine theta. Okay, so I have everything in terms of cosine and sine. There's nothing else in that problem now except for cosine thetas and sine thetas. Now I want to kind of think about how can I possibly simplify this down. Now if I look at this and think of it in terms of just fractions, so I'm subtracting two fractions, then I know that I have sine theta and cosine theta in the bottom of that first fraction, because since those two fractions are multiplied together, they could easily be written as one single fraction. So I could write this as the numerators multiplied together is 1 over the denominators multiplied together would give me sine theta times cosine theta. And then we're subtracting cosine theta over sine theta. So like I said, if we think about this just in terms of fractions, I'm subtracting two fractions. In order to subtract fractions, I must have a common denominator. So how can I make those denominators the same? Well, the first denominator has sine times cosine. The second denominator only has sine. So if I were to multiply that times cosine theta, that would then give me the same denominator. So if I multiply the denominator of that second fraction by cosine theta, then I have to also multiply the top, the numerator of that fraction by cosine theta, because then technically I'm just multiplying by 1 and I haven't changed the value of that fraction. So then if I simplify that a little bit, then I have 1 over sine theta cosine theta minus, and then in the numerator of that fraction, I have cosine theta times cosine theta. And anytime you multiply two of the exact same things together, we can write it as that thing squared. So we actually now have cosine squared theta. And then in the denominator, we have sine theta, cosine theta. So now that our denominators are exactly the same, we can write this as a single fraction. So we know that our denominator of that single fraction is going to be sine theta, cosine theta. And then the numerator, if we combine it, well, we have 1 from the first numerator minus cosine squared theta from the second numerator. And then I say, that could maybe be a version of one of my Pythagorean identities. So if I take that main Pythagorean identity, which was sine squared theta plus cosine squared theta equals 1, and I manipulate it, I can get it to look like this on one side. So in order to do that, I want to have 1 minus cosine theta, which means I can take this and I can move it to the other side. I'm going to subtract cosine squared theta, which would then leave me with sine squared theta by itself, and then it would equal 1 minus cosine squared theta. So that tells me that where I see 1 minus cosine squared theta, right here, I can replace it with sine squared theta. So I'm going to replace that numerator with sine squared theta, and then it's going to go over sine theta, cosine theta. And then I think, I have sine on both top and bottom. Now, I do have to be careful. I can't just say, hey, got a sine here, got a sine here, I'm going to cancel it, because remember, the numerator is sine squared theta, which is technically 2 sine thetas multiplied together. So if that's actually sine theta times another sine theta, and then our denominator is sine theta times cosine theta, now I can look at this and say, oh, I have a sine theta here, I have a sine theta here, those can cancel, and I'm left with just sine theta over cosine theta. And then that happens to be one of my ratio or quotient identities. So sine over cosine is the same thing as tangent. So this simplifies to just tangent theta. So we do all of that and we simplify as much as we possibly can. Now, I've got it much more broken down here than I do on my notes on Canvas, but hopefully that kind of helps you understand where everything has come from. Now, like I said, when you first start this, it's going to be tough, and it's going to take you some time to do these, but you've got to practice to get good. All right, so that was that first one. Let's move on to number 4. All right, so we're going to simplify this expression. Secant x minus tangent x times sine x. So the first thing we do is see, do they have anything in common that I can factor out? No. One is secant, one is tangent and sine, nothing in common. I can't use a Pythagorean identity because nothing is squared. So I'm going to change everything to sine and cosine. So I know that secant is the same thing as 1 over cosine. So secant x is going to be the same thing as 1 over cosine x. Then I have minus, then I've got tangent x. Well, tangent is sine over cosine. So this will be sine x over cosine x. And then times, well, that's just sine x. So sine x doesn't have to be changed because it's already sine. But I am going to go ahead and put that over 1 because we're dealing with fractions. So I have these two multiplied together, which means I can put them into a single fraction. So if I do that, I'm going to leave this first fraction the way it is, 1 over cosine x, but then I'm going to have minus, and I'm going to combine those two into one single fraction. So in the numerator, I have sine x times another sine x. Well, that's sine squared x. In the denominator, I have cosine x times 1. So that's just going to be cosine x. And then when I look at my two fractions, I notice, hey, I already have a common denominator. That's great. That means I can go ahead and combine these into a single fraction. So I know that my common denominator is cosine x. Therefore, that's going to be the denominator of my combined fraction. Now, the numerator is going to take the numerators from the two individual fractions and put them together. So I have 1 from the first fraction minus sine squared x from the second fraction. And then I think, I have 1 and sine squared. It is possible that that is a version of my Pythagorean identity again. So I take that main Pythagorean identity, which is sine squared, and we're going to have x this time instead of theta. It's still representing an angle. It doesn't matter. So sine squared x plus cosine squared x equals 1. So can I manipulate this to give me this on one side? Yes, I can. In order to do that, I need it to have minus sine x. So 1 minus sine x means I need to take the sine x and I need to subtract it to the other side. So then that's going to give me the cosine squared x by itself, and then that's going to be 1 minus sine squared x, which means anywhere I see this, like here, I can replace that with just cosine squared x. So the numerator of that fraction will become simply cosine squared x. The denominator is cosine x, and then I see, I have cosine on both the top and the bottom. However, remember, cosine squared x is really cosine x times another cosine x. And then if that's over only a single cosine x, then the cosine x in the denominator will cancel with one of the cosine x's in the numerator, and therefore we are left with just a single cosine x with technically a 1 in the denominator, but you don't need that. So it simplifies down to just cosine x. All right, so that was our second trig identity problem. So hopefully we're kind of able to follow this, and like I said, it's not going to be super easy at the beginning. You're going to struggle a little bit, but just keep practicing and you'll get there. All right, let's take a look at something else. So we need to simplify. Now this time, when we simplify, I've got two fractions. So just like in the other two problems, when I converted them to sine and cosine, I ended up having two fractions. And so I always tried to get a common denominator so that I could combine it into one fraction. I'm going to do the same thing here. Now I notice that my current denominators are 1 minus sine x and cosine x. Now those are not squared, so I can't use a Pythagorean identity. What I'm going to do is just get a common denominator. So if my denominators are completely different, then I simply multiply them together to get my common denominator. So that means that the first fraction would have to get multiplied by cosine x on both the top and the bottom. Actually, I'm going to put it in front where I have more room. So I'm going to have cosine x and then cosine x, because then I've technically just multiplied by 1. Then the second fraction is going to get multiplied by 1 minus sine x, and then the same thing on the top. So then I'm going to go ahead and put this in parentheses because that's a binomial, which means right here I have a binomial times a binomial, so that's going to actually have to get distributed out. Not as bad as it looks, by the way. Okay, so then I'm going to go ahead and kind of simplify these fractions. I know that I'm going to have a common denominator, and that common denominator is going to be cosine x. So cosine x times 1 is just cosine x. Actually, I'm going to leave them split. I may need to do that later, but for now, I'm going to leave it split. I'm just going to have cosine x times 1 minus sine x. So that's my common denominator. Now I do want to go ahead and multiply out the numerators. So in that first fraction, I have cosine x times sine x. So actually, since this is one term, then I'm actually going to combine that with the cosine instead of the sine. Let me get rid of that arrow. So I have a single sine x, so I'm going to leave that. And then I have cosine x twice, which means that is cosine squared x. Then I'm going to have minus, and I move on to my second fraction. Now this is where we have to actually distribute it out, because I have a binomial times a binomial. So then, some of us like the box method, some of us FOIL it out. Whatever works for you is great. So if we do the box method, then I have 1 plus sine x times 1 minus sine x. And if we think about everything we've ever multiplied that has a different sign in the middle, we should expect for our middle terms to cancel out. So let's test it. In the first box, we have 1 times 1, which is 1. In the second box on the top, we have 1 times sine x, which is just a positive sine x. Then on the bottom row in the first box, we have negative sine x times 1. That's negative sine x. In the second box on the bottom row, we have negative sine x times positive sine x, which is a negative sine squared x. And then we can see, definitely we have those middle terms cancel. So that simplifies to just be 1 minus sine squared x. So when I multiply this out, I get 1 minus sine x. Now I have to be careful though, because I have this minus here. So I'm going to go ahead and just write it out the way it is. So I have minus, and then that multiplies out to be 1 minus sine squared x. So this simply went here, behind the minus. So then, let's see what we can do from here. Well, first thing that I notice is this is a version of my Pythagorean identity. Because if I go off to the side and I fiddle around with the original Pythagorean identity, sine squared x plus cosine squared x equals 1, then if I subtract sine from both sides, I can get this. So that would give me cosine squared x equals 1 minus sine squared x. So that means that I can replace this with cosine squared x. So that's where we're going to go next. So we're going to keep the sine x times cosine squared x, and then we're going to subtract. This whole thing becomes just cosine squared x. Then we're going to keep our denominator, cosine x times 1 minus sine x. So we're thinking, okay, well, I've got some things in common here. Oh, and one other thing I want to point out is right here. You cannot cancel anything there because the denominator is 1 minus sine x. The numerator is 1 minus sine squared x. Those are not the same things. You cannot cancel out there. However, if we look at this fraction we have here, I notice that in the numerator, both of these terms have cosine squared x, which means I could factor cosine squared x out of that. So if I factor cosine squared x out of that binomial, then in parentheses, I would have left from here, if I factor out the cosine squared x, that leaves me with just sine x. And then minus from here, if I factor out cosine squared x, I'm left with just 1. Then we keep our denominator. So we have cosine x times 1 minus sine x. And then I think, okay, so these two are almost the same, but not quite. If they were a plus, I could say they're the same, but minus, it's not the same thing. However, let's take this and let's kind of go off to the side, and we're going to manipulate it a little bit. So we're going to take this over here. We have sine x minus 1. So I can, if I want to, I can switch this around and say that's negative 1 plus sine x. And then I say I could factor out a negative 1, and that would leave me with positive 1 minus sine x. And then that now matches this for us to be able to cancel. So let's take this and bring it back in and replace that. So we're going to have this cosine squared x that we factored out, and then that sine x minus 1 becomes negative 1. Ooh, let me put that in blue. Becomes negative 1 times 1 minus sine x. So we've got all the same stuff. We've just kind of broken it up a little bit. Then our denominator is still cosine x times 1 minus sine x. And now finally we can say, all right, so I have 1 minus sine x and 1 minus sine x. Those can now finally cancel. So then in the numerator, all I have left now is cosine squared x times negative 1, which really is just negative cosine squared x. In the denominator, all that's left is cosine x. And then I say, I have cosine on top and bottom, which means I can do some canceling. However, be careful. The numerator is technically cosine times cosine. There are two of them there. That's what squared means. So this cosine on the bottom will cancel with one of the cosines on the top and leave you with just cosine x, and don't lose your negative. Because remember, this was negative 1 times cosine x times another cosine x. So this cosine on the bottom canceled with one of these cosines and left us with negative 1 times cosine x, which is just negative cosine x. So that is your simplest answer. So as you can see, sometimes these can be a little bit more complicated, and sometimes they're going to be nice and easy. You'll have some short ones, you'll have some long ones, but the big thing is follow your identities and just keep working as you can. Another thing is there is not one right way to do these problems. There are multiple ways that you can approach this problem and get to the exact same answer. You just want to keep going until you get it as simple as you possibly can. Okay, so let's take a look then at one more of these, and then we'll look at a little bit different type. So for this one, we have two fractions added together that we need to simplify. So we're going to start this a lot like we did the last one. So we have two fractions with totally different denominators, which means we want to get a common denominator, meaning we didn't need to multiply each fraction by the other fraction's denominator. So for this first one, I am going to multiply this denominator by cosine x, which means that I also have to multiply the numerator times cosine x. Then the second fraction is going to get multiplied by this. So 1 plus sine x, which means the numerator also has to be multiplied by 1 plus sine x. Okay, so now that I have the exact same denominator, I can go ahead and combine these. So I'm going to have one single fraction with that common denominator. Now we're going to look at what can we do with the numerators. Well, in the first fraction, I have cosine x times cosine x, so that becomes cosine squared x. Now in the second denominator, I am going to have to multiply that all out. But this time, the middle term is not going to cancel because those two have the same sign. Remember back here in the last one, they had opposite signs, which is why that middle term canceled out. Not going to happen for this one. So if I multiply this one out, so I'm going to have 1 plus sine x times 1 plus sine x. So on the first row, I have 1 times 1, and then I have 1 times sine x. On the second row, I have sine x times 1, and then I have sine x times sine x, which is sine squared x. When I go to combine this, those sine x's don't cancel, they combine together. So I have 1, then I have plus 2 sine x's. So just like if that was a normal x, if these were both just plain old x's, we would add them together and get 2x. Same thing when it's sine x. I have sine x plus another sine x gives me 2 sine x. And then I have plus my sine squared x. So we use a lot of algebra in this as well. So then I'm going to go ahead and put that into my fraction. So I have the numerator from the first one plus, and then the numerator from my second fraction is all of that stuff that we multiplied out. So 1 plus 2 sine x plus sine squared x. And let me extend my fraction here. Okay, so it usually looks worse before it looks better. Now, we have to think outside the box a little bit. I see some squared stuff, which tells me I have the possibility of using a Pythagorean identity. Well, I cannot take this and say that that's sine squared, because remember, my original Pythagorean identity was sine squared plus cosine squared equals 1. So if I try to get cosine and 1 on the same side, something's going to have to be negative, not added. So that doesn't work. However, I said cosine squared plus sine squared, or the other way around, sine squared plus cosine squared, either way, added together gives me 1. Well, I can see that I have a cosine squared x here plus a sine squared x here. So if I were to do some arranging and put those together, then those together will give me 1. So if it helps you, you can actually rearrange. If you can see it the way it is, great. Go for it and save yourself some writing. So if you can see it the way it is, those two together, cosine squared x plus sine squared x, will give me just 1. And then, let me make that one green. Then you still have all of this as well. So you have plus another 1 plus 2 times sine x. And then that's going to go over my common denominator. Now, if you have a tough time seeing it with them separated, then go ahead and rewrite it. So I'm going to go ahead and rewrite it. I'm going to put this step in blue because this one is not absolutely necessary, but for some people it really helps. So I'm going to go ahead, I'm going to leave my cosine squared x in front, but then I'm going to rearrange and I'm going to say plus sine squared x, and then I'm going to put this stuff behind it. So plus 1 plus 2 sine x. And then I can see, oh, cosine squared plus sine squared, that gives me 1. So that's where that came from. And then I have this stuff just followed down. Okay, so hopefully that kind of helps you see it. So we're going to continue on from right here. So I have 2 1s multiplied together, so that gives me 2. 1 plus 1 is 2, plus the 2 sine x. Still have it over my cosine x, oops, forgot my parentheses, times 1 plus sine x. And then in the numerator I can see, hey, both of those terms have 2, which means I can factor out a 2. So if I factor 2 out of the numerator, then that leaves me with 1, because 2 divided by 2 is 1. And then if I factor 2 out of here, that leaves me with just plus sine x. So keep my denominator the same, cosine x times 1 plus sine x. And now I say, I have the same thing on top and bottom, exactly the same factor, which means the 1 plus sine x here can cancel with the 1 plus sine x here. And that gives me 2 over cosine x. Now, this one you have to think about a little bit. Some of us are going to see this right away and some are not. I have a cosine in the denominator. So think back to our identities. So if I have a cosine in the denominator, then that is the same thing as secant. Think reciprocals. Now, I don't have 1 on the top of my fraction. I have 2. Let me get back here. Here we go. I have 2. So if it helps you, think of this as 2 times 1 over cosine x, because technically that's 2 over 1. That's the exact same thing as 2 over cosine x. And then we can see that this is actually just secant. So then I have 2 times secant x. So if that helps you, great. But basically, if you see this cosine in the denominator, you know that you can flip it up to the numerator and it becomes its reciprocal function, which is secant x. So when I flip it up with the 2, it becomes 2 times secant x. And that's about as simple as we can get it. All right, so we have 2 last problems to go over. And they're a little bit different. So this one says to rewrite that fraction as an expression that does not involve a fraction. And so what we want to do here is we want to realize that this fraction is awfully close to a Pythagorean identity. Not exactly, but it kind of resembles a Pythagorean identity. So I'm going to start with my fraction. So 1 over 1 plus cosine x. Now, I know that my Pythagorean identity of cosine squared x plus sine squared x equals 1 can be manipulated, and I could have that as 1 minus cosine squared x equals sine squared x, because I just subtract that cosine squared x to the other side. So if I can find a way to turn this into this, then I could then get my denominator to be a nice simple sine squared theta. And so that's kind of always our goal. When we have a complicated denominator like this that has more than one term, we want to try to figure out how to make it to be just one term, because that makes our job easier. Now, I want to think about some of the things that we've done in algebra. We know that when we were back in algebra, when we were simplifying fractions that had radicals in it, we always multiplied by the conjugate of the denominator, and then that would simplify so that our radical went away. We did the same thing when we had I in the denominator. We're going to do something very similar here. We're going to multiply by the conjugate of the denominator. And remember, a conjugate means that it is exactly the same thing except the sign in the middle. So the conjugate of this is going to be 1 minus cosine x, and we're going to multiply that on both the top and the bottom. Now, the reason that we want to do that is because these opposite signs are going to make that middle term cancel out, and when we're done, we're actually going to end up with this. So that's kind of our goal. So multiplying by the conjugate allows you to turn that not quite a Pythagorean identity into a Pythagorean identity. So when we do that, we know that the numerator is now going to be just 1 minus cosine x, but the denominator is going to become that Pythagorean identity. And let's prove it. So if I go over here and I multiply those out, so I'm going to do 1 plus cosine x times 1 minus cosine x. So in the top row, we have 1 times 1, and then we have 1 times cosine x. In the bottom row, we have negative cosine x times 1. Well, that's negative cosine x. Sure enough, those cancel. And then we have negative cosine x times positive cosine x, which is a negative cosine squared x. So then all we have left is 1 minus cosine squared x. So sure enough, that becomes 1 minus cosine squared x, which we know 1 minus cosine squared x is the same thing as just sine squared x. So that's the next thing that we want to do with that. So we want to take that 1 minus cosine x, and then that 1 minus cosine squared x is going to become just sine squared x. And so you think, okay, this isn't making things simpler, but it's coming. Now, I have two terms on top, 1 and I have cosine x. However, I now only have a single term in the denominator, which allows me to very easily split this into two separate fractions. So I'm going to have my first fraction is going to be 1 over sine squared x. So 1 over sine squared x. Then I'm going to have minus, and then my second fraction is cosine x over sine squared x. Okay, so I still have fractions. Remember, our goal is to get this simplified to something that does not have a fraction. So for this first fraction, think about reciprocals. I know that sine is the reciprocal of cosecant, or cosecant is the reciprocal of sine, which means that 1 over sine squared x can be written as cosecant squared x. Then let's take a look at our second fraction. Now, I have a single cosine on the top. I have a sine squared on the bottom. So remember that sine squared means the same thing as sine times sine. So then what I want to do is I want to separate this into our two separate signs. So I'm going to have two fractions multiplied together, and they both have sine x, because sine x times sine x is sine squared x. Now, the cosine is going to go on the top of one of them, and if the cosine goes on the top of one of the fractions, then what do I put on the top of the other fraction? Well, just a 1, because cosine x times 1 is cosine x. So these are multiplied together. Now I can start simplifying. So I already have the cosecant squared x. That's not a fraction. Remember, our goal is to write this as not a fraction. Then we want to use our quotient or ratio identities and decide how can I rewrite cosine x over sine x. So if you look at your identity sheet, cosine over sine is the same thing as cotangent. So I can write that as cotangent x. And then 1 over sine x is the same thing as cosecant x. And there we go. So we have rewritten this to where there are no longer fractions. Now, we could, if we wanted to, we are able to factor out a cosecant because both of those terms have cosecant, but remember, our directions just said to rewrite it without fractions, and we've done that. So once we get it there, there's no need to do anything else. We've done what it asked us to do. Alrighty, let's take a look at one more, and it's going to work similar to what number 7 did. So for number 8, notice on the bottom I have 1 minus sine x. I know from number 7 that I can multiply by the conjugate of that, and it will give me a version of my Pythagorean identity in the denominator, which is what I want to do. And there are actually 2 ways to do this, so I'm going to show you both. So let's start with this one. So we're going to take our cosine squared x over 1 minus sine x, and we are going to multiply by the conjugate. So the conjugate of this is 1 plus sine x, so I have to also multiply by that on the top. So when I do that, I'm going to go ahead and I'm going to leave the numerator the way it is for the moment. I may mess with it later, but for now I'm going to leave it. And then I know that the denominator of 1 minus sine x times 1 plus sine x is going to end up giving us, when we multiply it out, 1 minus sine squared x, because those middle terms should cancel out. And then I know from my Pythagorean identity that 1 minus sine x is actually the same thing as 1 minus sine squared x is the same thing as cosine squared x. So I'm going to leave my numerator the way it is. And then I know that my denominator can simply be replaced by cosine squared x. And then I see that my fraction has a cosine squared x on the top and the bottom, which means those can simply cancel out, and we are left with just 1 plus sine x. So we no longer have a fraction. We're good to go. Now, there is another way that you can do this same problem. Most people are not going to see this as readily as the first way, but some will, and it is a very legitimate way to do it. So if I take that same beginning fraction, oh dang it, so if I take cosine squared x over 1 minus sine x, then basically this is kind of in a way working backwards, kind of. I know that cosine squared x could be part of a Pythagorean identity. And so if I choose to do it that way, then I'm going to change the numerator. I know that cosine squared x, if I fiddle with my Pythagorean identity, is the same thing as 1 minus sine squared x. Then I have that over 1 minus sine x. And then if we're thinking about some of the things that we've done previously, we know that this could be achieved by multiplying 2 conjugates together. So we're going to basically undo that. So we know that that could be achieved by doing 1 plus sine x times 1 minus sine x. So we're basically multiplying in reverse. And then we have our denominator, which is 1 minus sine x. And then I can say, I have a 1 minus sine x here, and I have a 1 minus sine x here, which leaves me with just 1 plus sine x. So either way, I am coming up with the exact same answer. Most people are going to see this better than they will see this, but some may see the other way. So whichever way works for you, that's how you should do it. All right, so that is 5.1, and I know that it seems very foreign. It is a very different way of thinking, and all I can say is don't give up, don't get frustrated, make sure that you practice, and we will go over this several times, and we will be able to get it. Do not give up, keep trying. All right, I will see you guys